So, welcome to class 52. So, in the last class we were actually looking at so I started by saying let us take one property into consideration, and that is refractive index, right. So, I said let us look at the refractive index, and refractive index is also a complex number, right. So, if I go back and show you, so I took refractive index as NR plus INI, and so refractive index, the imaginary part is dissipative and the real part is conservative again. So, in terms of the electromagnetic energy that you store and you dissipate, right. And so if a light passes through medium, refractive index is so is the quantity that one considers that is used to tell me how I am modulating this light, right. Now, for example, so the real part, if I look at the real part, so and the imaginary part. So, the imaginary part we said is going to reduce the amplitude of light or reduce the intensity of light, and so the imaginary part of refractive index Ni is also what is called the extinction coefficient, or that is related to absorption coefficient that absorbs certain intensity of light, right. Now, what is the real part of refractive index doing? The real part, right. So, inside a material, a light that is incident which has so let's put it here, let's write it again. So, a light that is incident into the material that has e power minus I omega t times e power I k x minus omega t, that is what is incident into the material, and so it is this is with an amplitude a naught, right. So, then the a naught is actually deteriorating. So, inside the material, once it comes out of the inside the material, right. So, at this entire thing is the material, and at a position x, if I look at what is the wave function, what is the waveform of this light, it is going to be a naught divided by 2 pi e power 2 pi by lambda Ni, right. So, this is the absorption that I will have, times it is still the propagating part is there, that is just given as e power I. Now, k nu, right. So, I am modulating the k, right. So, what is the nu k? Nu k is also given as so k nu is equal to the older k vector divided by n r, right. So, the new the wave vector itself is modulated, right. Inside the material, wave vector of the propagating wave, right. So, this wave is propagating as well as attenuating, right. So, this wave is so I said this wave inside the material, it is propagating spatially as well as it attenuates, right. So, within some attenuation length, okay. So, this is how the wave is propagating, and if I look at the propagating wave vector k is different from the the propagating wave vector which is in vacuum. This is in vacuum, this is inside the material, okay. So, I am changing the k, which means I am changing the momentum, right. So, k is the same as k is the wave vector, and h cross k is nothing but the momentum, right, momentum of photon. So, so by changing k, I am changing the momentum of photon that is incident, of momentum changing the momentum of a photon that is incident on the material, right. So, this process where I incident some particle, and that particle with a momentum p, and then so it goes off with another momentum p dash, right. So, this process where momentum changes, this process is called scattering, right. I am scattering light, in other words use so I am scattering light, and the corresponding quantity for scattering, right. So, the corresponding property for scattering is the real part of refractive index. Okay. And the corresponding quantity that I want to use for absorption or extinction is the refractive part of is the imaginary part of refractive index, right. This is scattering. In fact, if I want to be more precise, I am going to call this elastic scattering. So, I am not losing any energy, I am just scattering photons, right. So, this is the conservative part of refractive index, and this is the dissipative part of refractive index. Okay. So, we said all right. So, this is how light works, right. So, the refractive index works, and then I said something like, let us do this experiment to let us do this hypothetical experiment where I shine an electric impulse, right. So, this is an impulse that I am shining with electric field of certain value E naught for a time t, right. Then I looked at its Fourier, so this is shown on a material. So, in the frequency spectrum it is going to look like this, right, and then when I shine light of all these different frequencies in the frequency spectrum onto my material, then my and then I tell you that my material has two states where it can absorb, right. So, it can absorb light only at frequency omega naught, right. So, this is the absorption spectrum of my material, right. So, as a function of omega, my light is absorbed only at this frequency. Okay. So, if that is the case, I took the inverse Fourier transform of this frequency and I said, okay, inverse Fourier transform is this sinusoidal wave, right. So, the light that is detected then, right. So, I said what is the light that is detected? The light that is detected in Fourier space is just going to be so omega naught subtracted from the rest of the spectrum. So, the rest of the spectrum is not so this is just a scattered spectrum, this is not, there is only scattering there is no absorption, right. Only absorption, this is for omega not equal to omega naught. Okay. For omega equal to omega naught, there is only absorption, right. So, for the rest of the frequencies there is only scattering, which means my momentum changes, that is okay. When I incident a light of this frequency, the momentum changes inside my material when it goes inside my material, that is okay, but energy is not being dissipated, energy is not being taken away, right. But here only at this frequency the entire energy that is in that light is carrying in that frequency is absorbed by the material. Okay. Then if I reconstruct what is supposed to be my time domain signal, my time domain signal has this weird profile, right, where so this is t equal to 0, even at less than t equal to 0, even at less than t equal to 0, I see something, I see a signal. So, what is this doing? This we said is violating causality, that is I push you but you do not fall, sorry, I push you but you already fell before I push you, right, and now you are accusing me of being the reason for you falling down, right. So, that cannot happen, right. So, a court of law will not accept that sort of an explanation, right. So, there should be causality and so this sort of a thing violates causality, right. So, indeed that is not how processes happen actually, right. So, so then it turns out that so I have my light which is so absorbed only at this frequency, right. Okay. So, light is only absorbed at that frequency, but it turns out that this cannot happen because absorbing light at this frequency sort of violates causality, right. So, what it does is, okay, I will absorb at this frequency, but all the other the Fourier transform or this signal at all the other frequencies will know about this, right. So, I am absorbing at omega naught, but the frequency spectrum, okay, of scattered light, and by scattered I mean elastically scattered light, at all the other frequencies readjust themselves, to preserve causality. Okay. And so if that readjustment does not happen, then causality is broken, right. As a result, so what did I say this is? This is related to the property of interest is Ni, and the property of interest Ni at omega naught, right. So the property of interest in all the other frequencies is Nr at those frequencies, right. That I have an Ni at omega naught, right. So that I have an absorption or extinction at omega naught is an information that all the NRs at different omegas should know, right. So that I have an absorption at some frequency is known to all the entire frequency spectrum. Okay. So you have to so the transform or the absorption should work in such a way that if I have absorption at an at a frequency omega naught, this information should be transmitted to all the other frequencies, and all the other frequencies should sort of readjust themselves, right. So if I have something like this, okay, so and then I put my black mark is where, or I erase this part, a bit of this, let us say, okay, that is not good. Okay. So then I say that this does not exist. So wherever I put black, that frequency does not exist. Okay. But this cannot be the spectrum. So everything else, right. So I am going to draw it in blue, should have readjusted itself, right. So this entire spectrum should have readjusted itself such that that remains like that, but so everything else sort of something happens, right. So not exactly in the same way, but there is going to be a readjustment of the scattering refractive indexes also, of the scattering, right. So that I am absorbing light is known to scattering, right. That Ni exists at a frequency omega naught is known to Nr at all the other frequencies, at every frequency, right, at every frequency. Okay. Now this is what relates the imaginary part to the real part. So you have to make these functions causal in time, right. So in the time domain, right, the response functions should follow causality, and that means that Ni of omega and Nr of omega are related in a certain way, right. So this is the math, so they should be mathematically related, right. So that so I retain that causality, and physically it means that if I am absorbing at some frequency, that absorption, that information should so sort of the weights across all the other frequencies for the scattering, right, should readjust themselves, right. So this is what this experiment is saying, this hypothetical experiment is saying. Okay. Now how does it readjust itself, right. So this is not just valid for Ni and Nr, this is valid for any property, should be causal in nature, which means the properties R is a response function, R the real part is related to the imaginary part through what is called a causal transform. Okay. So we will look at so this is just I am not going to give you all the details about what causal transforms are, but I am just going to write down the formula, right. So I am not going to go into the details of what how this comes up, just like I wrote down the formula for Fourier transforms and said so in this course you just accept the fact that these are Fourier transforms, right. But to preserve causality, the property should follow some sort of causal transform. Okay. So now let me ask the question, what is a causal transform, or or this has a name, this is also called Hilbert transform. Okay. Now, mathematically if I have a function phi of omega, right. So, that has phi r omega plus phi I omega, I phi omega, right. For phi to maintain causality, to have causality in time, right, causality in time, what we need to have is that phi r of omega is a Hilbert transform of phi I omega, which means phi r omega can be written as 1 by pi, right, integral of phi I, so nu d nu by nu minus omega, and I integrate over nu goes from minus infinity to infinity, right. I will tell you why, so I take what is called the principal value of this, but I explain what this means later. Okay. So for now this is the formula, right. So this is the formula for a Hilbert transform. So phi r is the Hilbert transform of phi I, which is defined in this fashion. Also phi I is the Hilbert transform of phi r. So both of them should be Hilbert transforms of each other. Okay. So okay, so let me rewrite what phi r equal to. Phi r is the principal value of 1 by pi integral minus infinity to infinity phi I nu d nu divided by nu minus omega, okay, and d so and phi I is the principal value of 1 by pi integral minus infinity to infinity phi r of nu d nu by nu minus omega. Okay. All right, good. So now I have an issue here, right. So this is phi r at a frequency omega, this is phi I at a frequency omega. Okay. So in some sense, right, so I don't like the fact that so this integral goes from minus infinity to infinity, right, and which means phi I needs to be defined at frequencies which are also negative, right. So both phi i's and phi r's, this formula would mean that phi i's and phi r's need to be defined at negative frequencies. You can interpret what negative frequencies mean. Actually, if it is rotating clockwise, it is positive frequency, rotating anti-clockwise, it is negative frequency. There are such interpretations that exist, but so I am so there is a bit of uncomfort, right. So discomfort in trying to understand what this negative frequency is. So let us make everything positive, right. So I want an integral phi r of omega should be an integral from 0 to infinity of having phi I nu d nu and so whatever terms, right. So I want to make it in this fashion, right. So not minus infinity to infinity. Okay. So now I use the fact that okay, so so phi, if I look at phi t, right, so phi in the real time, right, so phi in time, right, so this is in time domain. I use the fact that phi is a real valued function, right. Now capacitance, for example, cannot be complex in time, it can be complex in frequency, and we have an interpretation for that, but in time all these properties are real, right. So there is no imaginary component for these properties, right. So phi of t is a real valued function, right. So then if I look at what phi of omega is, integral phi of t e power minus I omega t dt, right. Now what is integral phi star of omega, which is a complex conjugate of omega? Phi of omega can be complex, this is complex number, and complex number has a complex conjugate. So I look at the complex conjugate of t, I take e power I omega t or minus I minus omega t dt, right. So this is what I am going to do, and since phi t is real, right. So real numbers have the same so their complex conjugate is the same as the number itself, because what is phi t? Phi t equal to phi r t plus there is no imaginary part, right. So plus I times 0, right. So, phi star t should be phi r t minus I times 0. Okay. So, since this is 0, phi t and phi star t should be the same, which is phi r of t. Okay. So, so these are one and the same. So, I have phi star of omega is actually equal to so phi of t e power minus I minus omega t dt, right, and t goes from minus infinity to plus infinity, and so this minus I minus omega, right. So this is nothing but phi of minus omega, right. So I can just write it as phi of minus omega. So I have this property that phi star of omega equal to phi of minus omega, right. So okay. So this is the property that I am going to use. Now what does this mean? This means that so phi of omega, I am just going to write it as so phi okay, so phi of omega is phi real of omega plus I phi imaginary of omega, right. So phi star of omega will be phi real of omega minus I phi imaginary omega, right, and phi of minus omega is equal to phi real of minus omega plus I phi imaginary minus omega, right, and these two should be equal. What does that mean? That means that phi real of omega equal to phi real of minus omega, or phi real, right, is an even function in omega, right. Similarly, phi imaginary is an odd function. So, and then you have the second relation is phi imaginary of omega equal to minus phi imaginary of minus omega, right. So this is what you will get is an odd function in omega, right. So even function means it is symmetric about omega equal to 0, odd function is not symmetric or anti-symmetric about omega equal to 0. Okay. Now we can actually do this integral. So let us look at what phi r of omega equal to. Phi r of omega equal to 1 by pi integral minus infinity to infinity phi I of nu d nu divided by nu minus omega, right. Now I am just going to split it up into two integrals, and there is a principal value always, I am going to ignore it for now, right, and I am going to put it on later, right. So I have to write it as p of this, but the p assume that it is always there, right. So the p is assumed. Okay. So all right, so let us get back to this. So this is minus infinity to 0 phi I nu divided by nu square minus omega square nu plus omega, right, d nu plus infinity 0 to infinity, again the same thing phi I nu by nu square minus omega square nu plus omega d nu. Okay. And you can actually see that phi I nu. So if I replace so nu with something which goes from with minus some nu dash, right, and so nu dash, so I change the variable nu dash to minus nu. So I use a new variable where nu dash equal to minus nu, right, and nu dash then goes from infinity to 0 or 0 to infinity, right. So I can do that sort of a transformation, and so then I can actually show that phi I of minus nu equal to minus phi of nu, right. I can use these two facts, right. So I do a variable transformation, and I use the fact that this is an odd function, phi I is an odd function, then I end up with this integral and this integral, where the omega terms this integral will the omega terms will cancel off, and I will just get this to be 1 by pi 0 to infinity. I am going to change the limits from 0 to infinity, sorry 2 by pi 0 to infinity nu phi I omega divided by nu square minus omega square d nu, right. So, this is phi r of omega. Okay. Similarly, I can write phi I of omega in the integration limits which are from 0 to infinity now as just omega, omega comes out, omega is some constant because I am just looking at 1 omega, right. So, phi I, sorry, this is nu, phi r of nu, because now r of nu is an even function, right. So, you have to derive this yourself, it is an easy derivation, right. So, derive, prove to yourself. Okay. So, even this you can derive using these facts, right. So, nu dash goes to minus nu and so this integral limit changes from 0 to infinity, right. So, that is the second change, and you know the fact that phi I is an odd function and phi r is an even function. I use these facts to actually show that this is actually equal to nu square minus omega square. So, it is not a hard derivation to do. Okay. So, you can do it yourself, just sit at home and then write it properly, you will arrive at it. Okay. Okay, all right. So, that is nice. So, you know, so essentially at about you know nu equal to, so these are okay. So, these relations, right. So, where phi r is phi r is a function of phi I, right, in a complex way, right. So, it is not a very simple function, it is not just you know is a function of phi I, and phi I is also a function of phi r, or these functions are actually not functions, simple functions, they are nothing but it is a Hilbert transform, right. So, these sort of relations are what are called Kramers-Kronig relations. And what does Kramers-Kronig relation say? If I know the absorption spectrum, now I you know I do not consider absorption only at one frequency, right. If I know the absorption spectrum, so let me write this down in words, right. Okay, absorption spectrum means phi I as a function of omega completely, right, completely. Then I know the scattering spectrum also completely. So, I can do a scattering experiment or an absorption experiment, right. Right. So, I do not, both of them are interdependent on each other. If I know phi r as a function of omega, I can get phi I as a function of omega, right. So, both of these are transforms of each other. If I know one completely, I should know, right. So, I should not, so if I just know phi I at one frequency, right. So, if I know phi I at omega naught, I cannot predict phi r at omega, right. So, omega naught, because phi r at omega naught is actually equal to 2 by pi integral nu phi I of omega, phi I of nu divided by omega minus nu minus omega, nu square minus omega square, right. So, d nu, right. So, that is the formula. Yeah. So, I should know phi I at all the frequencies. For me to know phi r at omega naught, I should know phi I at all the frequencies, right. So, I should have the complete information about absorption. If I have complete information about absorption, I have complete information about scattering, or if I have complete information about scattering, I have complete information about absorption, right. Complete information meaning the entire spectral information. This is what is called spectral information, which means of the dissipative property complete spectral information of the dissipative property means I have complete spectral information about the conservative property and vice versa. So, these are not somehow independent, they are they are two sides of the same coin, right. So, these are phi I and phi r are not independent. This is what I have been saying all this while, right. So, scattering and absorption are related, dissipation and conservation are related, right. Or in other words, we said phi r, so statistically this comes from some sort of fluctuations in the order parameter. If I am talking about light, this is nothing but the scattering, okay, and phi I is nothing but the dissipation in order parameter, dissipation in energy, right. And if I am talking about light, this is absorption, right. So, now I am saying that fluctuation and dissipation are one and the same or are related, right. If I know the complete spectrum of this fluctuation property, I can predict what the dissipative property is. If I know the complete spectrum of the dissipative property, I can predict what the fluctuation property is, right. So, so you can go a bit further and derive what is called fluctuation dissipation theorem in statistical mechanics. We are not going to do that. We will stop here at Kramers-Kronig rules, Kramers-Kronig theorem, right. So, which says that scattering and absorption are related, and so in the next class we will start building up from this aspect onwards, right. So, we will look at what is this absorption, what is this scattering, so we will try to give a quantum mechanical spin to this. Both of them are related, so if system knows one thing, it will know the other thing. Both of them are the same property, right. They are different sides of the same coin in some sense. If I know complete spectral information, right. So, complete spectral information means frequency dependent information about one phi I know the complete spectral information about phi r, right, and so on and so forth, right. So, then we will actually see how to measure these things. So, to measure anything, if I measure absorption, for example, at different frequencies, then I will have all idea about the scattering at every frequency, right. So, we will look at how to do these absorption measurements also in the next next classes, okay. So, I'll take about 2 to 3 more classes to end this course, okay. All right. So, see you again in the next class. Thank you very much.